Good morning, here we are. Once again, it's the physics video lecture. psci 168 video lecture 10. Okay, we're in the middle of some great material right now. So let's see. Always want to start with a little bit of a review. And we've come quite a ways because we now know what energy is, what power is. So as our review, I will just put those concepts up again. You know, we have force, it's measured in newtons, it's a push or a pull, okay? And we had all this interesting stuff about structures. But right now we just need the simple version, the scalar version of force. Measured in newtons is a push or a pull. Work is force times displacement. You move something in the direction of the force, and that takes work. The units of work are newtons times meters, and that's the joule. So we have work, and I like this idea of potential energy being stored work. First of all, right, energy is the capacity to do work, which means to exert a force over some distance. And then potential energy, which I'm just abbreviating PE, is stored work. That's a good way to look at it. Stored work. We'll run with that. And this is where we have this example of potential energy. And I want to add a major one. Examples of potential energy. The first one is our grandfather clock that we're working on, right? Trying to figure out the grandfather clock. And I'm just going to write clock, by which I mean the grandfather clock. And the face of the clock is up here, and the stored work is simply that this mass, this weight of, say, 50 newtons, has been raised up a distance. So once the weight's been raised up that height there, that's stored work. And if you just let it sit there, it would be stored work. And if you let the clock run, it eventually goes down tick, tick, tick tock at a time till it's down at the bottom. So it's stored for a full week once you get the clock running. So we had stored work in the clock there. Now my second example is going to be a little more massive. By the way, how many joules was this? We said the work was, in this example, was 75 joules. I was going to run the clock for a week. Now, a major topic in this class that's coming up, you could say it's a central topic, is going to be hydropower. And in terms of the stored work, I'm going to get started right now. You know, there's water behind a dam. We have many of those in our own mountains here, but worldwide you have that. So you have water. And the power plant doesn't have to be at the base of the dam. It could be way down the mountain somewhere. So the difference, here, let me use blue. Let's imagine we have a cubic meter of water. Of course, there are many, many cubic meters of water in a lake. So we have 1 cubic meter of water, and the height that it is above the powerhouse is, we'll say 500 meters. We can have more than that. 500 meters is a good number. That's realistic. And the water runs down a big pipe. Okay. So potential energy of 1 meter cubed of water at h equals 500 meters. Okay, so that's well-defined problem here. So how much potential energy is that? Let's go on here. Well, first of all, 1 cubic meter, by the way, this is a meter, so that's a pretty big cube, okay, meter on each side. It's like this side of the table here, blocking off, and down to the floor. Cubic meter of water weighs approximately how many newtons? Okay, we're going to get the exact answer later on, but this approximation is close enough. It's approximately 10,000 newtons. 10,000 newtons. We'll learn later that's 1,000 kilograms times approximately 10,000 newtons. So, and we'll call that F. So, work is equal to F times H. That's going to be the potential energy is 10,000 newtons times 500 meters. Okay, we don't need a calculator for these. We have 10 to the 1, 2, 3, 4 times 5 times 10 to the 2, and Newton meters is joules. So our answer is 5 times 10 to the 6 joules. Okay, so that's 5 million joules. And we have a whole lake full of cubic meters, and you could say that lake with the water elevated above the powerhouse is potential energy. Okay. So potential energy, the answer here is 5 times 10 to the. Let me go ahead and write it in here, and then underneath here was the calculator. So that potential energy is equal to 5 times 10 to the 6 joules. And you're going to see how important our scientific notation and powers of 10 are, because these numbers are going to get large very fast. Okay, so this was the review in the sense of what potential energy is, stored work. Now, we're going to go into the study of motion for the following reason. Motion is involved when this weight in the clock slowly drops down. Motion is involved when the pendulum is swinging back and forth. Motion is certainly involved when the water comes tearing through this long pipeline. Okay. Motion is also involved in the example I gave the other day, where if we were going to drop a weight on a stake and drive it in, okay, we were going to drive something in, we knew that there was work involved, and yet as that dropped object was falling, it was just all about motion, and we have to learn about motion in order to understand how that motion could get turned into work again. So potential energy is stored work, energy is the capacity to do work, but we now need to study motion to get a complete picture of the whole energy business. So next, we have to study motion. So that's a whole branch of physics that has to be studied. That'll bring up another set of energy concepts, and then we'll have the more or less the complete picture. Well, it won't be that complete, but we're getting there. Good. So the study of motion. So I'm going to start that independent of the physics, just not independent of the energy idea, just motion, pure and simple. So let's just write down our list of concepts and kind of the program for what's going to happen in this chapter here. So we're going to do what are called the kinematic concepts. Position, velocity, acceleration, and so forth. We're going to study free fall. Okay. And then we're going to be able to build up the energy concepts. But, since we're going to be studying motion and we want to get some interesting examples of motion, we're going to do a section on satellite orbits. Satellite orbits around our Earth. And it turns out it's something that's really useful for our discussion. And first of all, we know how big the Earth is, we did that, and therefore we're going to be able to figure out how fast a satellite has to be moving in order to orbit. And in fact, I generally put that on an exam question like that. So we're going to do some pretty interesting and thorough discussion of motion before we finally bring it down to Newton's law, which is force and motion. And then kinetic energy. So kinetic energy, the energy of motion, is something that we need to complete our energy discussion, but we have to build our way through it, okay? Just so you see where we're headed with this. Entire physics education, 2 semesters worth. Okay, so to begin with the study of motion, I'm going to start with falling motion. Got an interesting demonstration for you here just on the tabletop. So what is the nature of falling motion? So falling objects. You throw a ball up in the air and it comes back into your hand. Tennis ball, right? Throw it up in the air, catch it. That's falling motion. On the other hand, I have in here, you could throw a hammer. You could throw a hammer up in the air. Watch out. And you could throw a feather up in the air. So there's different types of falling motion. We've got the hammer, tennis ball, the feather. Okay. So falling objects. Hammer versus feather. And I can do the hammer versus the feather. Try not to damage anything in here. It's all got to be on the tabletop. So I'll drop this onto my book. So the hammer versus the feather, which one hits the ground first? Okay. Hammer falls much faster. Okay. Tennis ball at this range is really about the same. Okay. You're not going to see any difference with the hammer and the tennis ball. If you were to drop this from a tall building, the hammer would probably win the race. Okay. But the feather seems to be a qualitatively completely different thing. Okay. Feather falls so slowly. So why? Why is the feather not fall as fast as the hammer? Okay. And it took people a while to come across the right answer. The feather experiences relatively more friction. Now the hammer has the same surface area as the feather facing the air here, but it has so much more mass that the frictional force on the hammer is negligible, whereas the frictional force on the feather due to air resistance is large. Okay? And by the way, you can take feathers, you can take crumpled up paper, flat paper, you can do all manner of things, and they all fall a little bit different. I'm just going to use this feather as an example. It's a good visible example here. Now, can I make the feather fall exactly like the hammer? Surprisingly, the answer is yes. So the feather does not stick to my notebook here. Okay, I'll take these notes out. Feather doesn't stick to the notebook at all. But if I drop the feather on top of the notebook, You guys can see this? If I drop it, it falls with the notebook. It's not sticking. It is not sticking, it's just falling with the notebook. So that's an amazing thing because it indicates that the nature of falling objects is the same for all objects. We thought the feather and the hammer were different, but when we eliminated the friction simply, okay, you know, it's so surprising that you really got to convince yourself it's not sticking to the book, it's just falling through the air because it's just falling without air resistance because the book's in the way. Okay. So if you were to take a feather to the moon where there's no atmosphere, it would actually fall straight down with the hammer. Okay. Hard to believe. But this demonstration is so important because we can say that things actually do fall the same. There is a law of free fall. Okay, so let's go ahead and write some of this down. Falling object hammer versus feather. If we can eliminate the friction, you think it's also called wind resistance or air resistance, then all objects fall the same. In the ancient world, they did not figure this out. This was around Galileo's time, 1500s, 1600s, that this was first discovered. Even though the ancients did measure the shape and size of Earth, they did not get this figured out here. So if we can eliminate the friction, then all objects fall the same. And what we do is we call it free fall if the friction is negligible. So that's what the expression free fall means. It's the type of falling that occurs when the wind resistance, when the air resistance is negligible. Okay. So important point here. And this is, so to speak, a law of nature here on Earth. All things fall the same. And not only on Earth. So the next question is, what is the nature of free fall? We want to figure it out mathematically, quantitatively, nature of free fall. So yeah, definitely try this demonstration. You can also just take a sheet of paper, if you don't have a feather around, just a flat sheet of paper on the book. You know, the paper's slow. Okay, but if you put it on top of a book, then it just falls straight down with the book. Okay. So yeah, this is a good demonstration for you guys to convince yourselves about free fall. Okay, so the next question, what is the nature of free fall, the mathematical law? What is the, I'll write here, mathematical law of free fall? Well, for that we're going to have to measure things. We have a ruler and we have a clock, right? We talked about the pendulum clock, we've got the ruler. So that's what we're going to use to get this figured out. Okay, let's see how we're doing. Time-wise, good. So what we're doing now, we just did point 2, we have to bring in the kinematic concepts. And we won't spend that much time with them, but I'll state them. Kinematics in one dimension So that could be up or down, or it could be horizontal, it could be on an incline. It's just one direction, one dimension. And the concepts are the following. You're just going to list them. There's something called the position, and that is literally just your location, say, on a number line. So this is the meter stick X, and we'll call that 0, 1, 2, 3, etc. Then we would indicate that we've got a 3-4 meter stretch right here, and the position is just where something is. So my example here, X equals 2.5 meters from the origin. Okay. The next concept is if you move something from A to B, it's called displacement. So displacement is, say I start at 1 and move to 2.5. So I'm going to go ahead and have a 0, 1, 2, 3, 4. And let's call this A and this B. So displacement, position, okay, position was X. Displacement is delta X. We could say it's X B minus X A. The difference. And by the way, it doesn't matter if B or A are in front or back of each other. It's just XB minus XA. And so in my example here, it's 4, this is meters, it's 4 meters minus 1.5 meters. So the displacement was 2.5 meters to the right. But it could have been, if I started at B and went to A, then it would have been XA minus XB, and it would have been minus 2.5 meters. So the displacement can be positive in one direction, and then it's negative in the opposite direction. But that's the displacement. And now we get to velocity. V is equal to delta x over delta t. Now the delta x we already defined as the displacement. The delta t is just a time. I don't have to even write the delta, but it's going to mean the same thing. Okay, so we can actually use these interchangeably. It's a distance, a displacement in position over a difference in time, or just over a time in general. So my example, and my units, for the units it's always a square bracket, and then we have meters in the numerator and seconds in the denominator. Okay. So that's our velocity. And by the way, this is very common for us. We always talk about miles per hour when we're driving. Okay. Miles is a length or a distance or a displacement, and hours is a time. So here we're having velocity in meters per second, and when we're driving we talk about miles per hour. Okay? Now the example I want to give, it's good in this classroom here, you can't see the extent of it, but it's actually a full 10 meters wide. Very close to 10 meters wide. Okay? And my example is going to be V is equal to 100 meters divided by 10 seconds. 100 meters is the length of the 100-meter dash in track and field. And 10 seconds is roughly the world record. It's 9.8, 9.9 something, close to 10. And so this gives us a good approximation of how fast the fastest runners can run, which is about 10 meters per second. And we can all go out there and try ourselves. We're probably not this fast. But so that gives you a good feel for velocity on human terms. And if you want to, you can look up the conversion for meters per second and miles per hour and kilometers per hour and everything else like that. or you don't even have to look them up, you can even figure them out yourself. We'll just go with meters per second for our basic unit of velocity. So good, we have position, displacement, velocity, and there's one more construct that we need, and that is acceleration. Acceleration, this one's trickier, but it's fundamental to physics, so we have to know it. The acceleration, letter A, is delta V divided by delta T. It's the change in velocity over the change in time, or just the change in velocity over time. Its units, square bracket, are meters per second in the numerator and seconds in the denominator. So we say that is meters per second squared. So the units, meters per second squared. This is going to play a big role. You know, it looks like you could just keep going, but physics tends to stop right here with acceleration. So that's the set of kinematic quantities: position, displacement, velocity, acceleration. You see how each one builds on the previous one. So a change of velocity, what is a change of velocity? We need some examples. You just write these examples down. So for example, you're in your car. The red light, now the light turns green, and you push on a pedal referred to as the accelerator pedal, and you start moving. So your velocity changed because it was 0 before, and now you're moving. So there's an acceleration. If you come to the next traffic signal and it's red, you're cruising along, and then you're going to come to a stop. Again, you were moving and you came to a stop, so your velocity changed. So the coming to a stop is also an acceleration. And it would have the minus sign in front of it. You could call it a deceleration, but it's still an acceleration. So we have these, we have examples for each one. Now let's look at the free fall problem. I'm just going to throw the tennis ball up and catch it, okay? It started at rest, it left my hand with a certain speed. So that was an acceleration that I gave the tennis ball. But when it left my hand, it was on its own. Okay? Left my hand, it came up, came back down, so it flew up, came back down. So after it left my hand, it was slowing down. Was it accelerating? Its speed was changing, its velocity was changing, so it was accelerating. It came to a stop, and then immediately after it starts picking up speed in the down direction. So it's the same as if I let go of it from here and it's picking up speed. Again, it's accelerating. So from that, we already know free fall is an accelerated motion. We wanted that law. Yeah, what's the mathematical law of free fall? Well, we already see it's an accelerated motion. So let's go ahead and write that down as an example. And we can do even better than that, but that's a beginning. Okay, so let's go ahead and leave that list up. So just based on the definition of acceleration, I'll number this 5. Actually, let's put these examples in traffic. That should remind you, you could write them down, what I just said, examples in traffic. Starting and stopping, free fall is accelerated motion. That's not all we can say about it, but we can say that. Let's see how far we're going to get today. Good. We have time for a demonstration. So now, this accelerated motion of free fall, it seems to be happening too fast for us to just study it with a ruler. You know, these concepts involve rulers and watches or stopwatches because they involve lengths and times, right? Lengths and times. But if we want to study this free fall here in the lab, it's just over so fast. So the first person to really study it was Galileo. And what we have to do is slow the motion down somehow. And what Galileo did was he just rolled things down an incline. Because he said, well, this incline is kind of like free fall, except I'm slowing the motion down. Okay. So rolling a ball down a hill. And then he said, well, if I make the incline steeper and steeper, it's still like free fall. And if I make it completely vertical, it is free fall again. Okay, so that was kind of the reasoning in physics, was taking that limiting case. So the first thing is, I'll just write Galileo, let objects roll down the inclined plane. Down the incline. But there's no clock involved, so you can measure these distances, but he didn't have a clock for them. So what he did was, to incorporate a clock, he did something very clever. He put some little impediment there in a groove on the track where it would make a click as it rolled by. Okay? So there's a click sound, click, and ditto here, ditto there. And so now if it clicks, that's his clock. But how is that a clock? It's a clock if you can make it click in an even rhythm, because then your own sense of rhythm is telling you that those are equal times. You don't have to know if it's a second or half second, you just have to know that it's equal. So that's how Galileo got, by the way, there was no good stopwatch back then, so he had to come up with something clever like that. So, even, or the sound of the clicks makes an even rhythm. And your sense of rhythm, that's an innate musical sense, and you could say that was the clock. i.e. a clock. And with that innate clock, you could then measure these kind of quantities. You have a ruler for the lengths, and you have the even clicks for the time. Okay, so can we do that? And the answer is yes. So let me make sure I have enough time, or else we'll do this next time. 33. Yeah, let's do it right now. So the last thing I'm going to do is what's called a drop chord. I'll demonstrate it, and this is one you guys can try at home as well. So the demonstration is called the drop chord. You know, building an incline and a groove and little clickers is not so easy. This drop chord is very doable. I'll show you what the ingredients are. You need a soundboard. It's going to be this can here. And these little clips are going to make a sound when they fall on the can. Okay. And I have a length of string. Always store your string on some kind of spool, otherwise you'll just have a tangle. I get a tangle anyway. Okay, let's see here. So normally with a classroom and a ladder, I can do a long version of this, but we're just going to do a short version. So I'll draw this on the board. Let's see if we can make this work. So I always anchor it with the pen at the bottom. Now I know the answer, so I can measure this out quickly. If we were doing this for the first time, like Galileo, it would take us some time to figure out the correct lengths. But let me describe what I'm going to do first. I have a soundboard here, and I have a string. And the string is just going to be anchored at the bottom there. I'm going to attach little clips in increasing distances. Okay. Because the free fall is accelerated, so this first one's going to hit and make a tone. Second one, third, fourth. If the spacing is correct, we're going to hear an even rhythm, even though the spacing is quite different. So that's what I have to do right here, and I have to remember the answer. I was claiming to know it. There's the first one. Here's the second one. I'll do 4 of these. See, I'm reading off the answers on my ruler here, or the numbers that I know it has to be. Okay, so this will make 4. So this is my drop chord. I have these 4 objects, these clips. And let's see if we can get an even beat, even rhythm. We can try this a few times. I just let go of it and see what we can see what the video picks it up. Ready? That was pretty good. Let's try it again. I heard it. I want you guys to hear it. It's rat-a-tat-tat, and you want to convince yourself, or you want to hear whether they're even or not. Very good. Okay, I'm going to tell you guys how to do this. I would recommend you guys try this at home too. Okay, let's more. That was a good one. Okay. 1, 2, 3, 4, evenly spaced. So there's our drop chord, and you get a string and you just clip something onto it, okay? These little paper clips. Good. Now, drop chord. I already wrote demo. So here's what we're going to do now. We have time. We're making a data table. Data. This was an experiment. Time, distance, fallen. And leave room for a third column right here. So the time was 0, 1, 2, 3, 4. We heard 4, and 0 was the instant I let go. Okay. So the distance fallen at 0 was 0. Now let me write down what I had put here. 5 centimeters, 20 centimeters, 45 centimeters, and 80 centimeters. That gave us an even rhythm. Now let's just take that 5 centimeters as a unit. So that would be 1. Then that went into 24 times. It went into 45 9 times, and it went into 80 16 times. Because this was an arbitrary unit of time, and this is a unit of length. And what do we see here? Let me go ahead and make a little room here. We can see that the distance fallen is like the square of the time, okay? If we were to keep going, then what would we have here? 25 and so forth. So you can build a longer string, and you can use different increments. It's as long as you build the distances as the squares, okay? So what we have is distance fallen is proportional to, so this sign means it's proportional to the time squared, or we can write d for distance fallen is proportional to t squared for time squared. And that means that if we divide both sides by t squared, we get constant. The fact that there's a proportionality means that distance divided by time squared is some constant. That's what proportionality means. So this is proportional to, okay, proportionality. And this is the law we were looking for. I'm going to end with this. I'm going to end with this and say what it means next time, okay? But this actually contains the law that we were looking for. And this is one of the only times in history and in your life that you can just get a law of nature in this basic of a fashion. So, as far as the homework goes, did I write down any homework yet for today? Drop chord. Go ahead and try to do a drop chord. You have these relations here. You drop it on a pan or something that'll make a nice ringing sound. What I did in this class last time when we were meeting, every student brought, actually not this one, but the similar one. Every student brought their drop chord to class, and we all did the rat-tat-tat and showed that it worked. Okay. So yeah, make a drop chord and then show me some picture evidence that you did it. How about that? That's all we'll do for today. We're well on our way, and this is fully rigorous, okay? This is rocket science. So I erased our list, but now that we have the drop chord, we're gonna get the law of free fall. And from the law of free fall, the satellite orbit is not very far at all. So we're gonna be in there in no time. So yeah, take your time on this, go over these concepts. If you can build a drop chord and make it work, that'll be nice too. Okay. Yeah, we'll call it a day. So see you next time. Good.